Hey guys, one more section to go after this. We are still in chapter 9, and what we're going to do is take a look at one of those nonlinear functions called a quadratic function. So a couple things you need to know about quadratic functions. The first, let's talk about our vocabulary. A quadratic function, let's see if we can get a black pen that works. A quadratic function is a function that'll be in the form of ax squared plus bx plus c. So sometimes we might see y is equal to ax squared plus bx plus c. If we're getting jazzy, we might see f of x is equal to ax squared plus bx plus c. I want you to kind of think back to the idea of what a linear function is. So here's our linear function. We remember it's y equals mx plus b, and we remember here b was the y-intercept and m was the slope. We don't really have that here. We do have a constant term here, c, and we will talk about when we look at some of the problems and some of the examples what c may do, and we can speculate about that. And I also like you guys to maybe play around with Desmos and see what you can do, but we'll get into that in a moment. And the other thing we can do is talk about what a parabola is, and what a parabola is the graph of a function in this form. Now let me go back to this function real quick. When we talk about having a quadratic formula, a quadratic equation or quadratic function, we need to be reminded that all of these values here are important. So we need to have an ax squared value most definitely. So a cannot be 0. Right? If a were 0, then this whole term would go away and we'd actually have a linear equation. So the caveat is that a, b, and c are all integers such that a cannot equal 0. And I'll write that down in math ease. A, b, and c are integers where a cannot equal 0. Because if a were equal to 0, then I would actually have a linear equation, and that bx plus c would really be my mx plus b. So that should get you thinking about what c is. If b was the y-intercept, what do you think c is? So we'll kind of look at that in our next couple of examples. So a parabola, now let's get to that, is when I graph any function that is truly a quadratic function, you're going to get a shape that looks like this. It's not really a U and it's not a V. It's kind of a combination of the two. It's a beautiful curve. They can be upside down or they can be right side up, meaning that their two arrows can be going down to infinity, negative infinity, or it can be going up to positive infinity. So those are the two vocabulary words that we need to keep in mind. Let's get started with at least some key concepts. So our key concept is that this is just as we mentioned before, this is exactly what a quadratic function is. When we graph it, it looks like this. Notice over here, if I were to write this in ax squared plus bx plus c form, I would have 1x squared, so a would be 1, plus 0x, b is 0 here, plus negative 4, right? So that's in the ax squared plus bx plus c form. Notice that a, b, and c are all integers where a does not equal 0. Even though b equals 0, we still create a quadratic equation or a parabola. So that's why we have this. Notice that our c term, the one that we were talking about, is negative 4. Do you notice anything about this graph and how that negative 4 might have an impact on this graph? Let's see if whatever you're noticing comes up in another example. So let's try example 1. So here in example 1, we're going to graph y equals x squared minus 2. So our expectation, recognizing that we're dealing with a quadratic function, is that we're going to get some kind of a parabola, right? So I'm going to just put that there. I'm not looking for a straight line. So it is not sufficient. Remember how when we were looking for linear equations, it was okay just to find 2 points, because 2 points make a line, find the 2 lines, or 3 just to be sure, draw a straight line, you're good to go. You're not going to be able to do that. You are looking for a nice curve. So we're going to have to plot a number of points in order to get the curve that we want. So we have to be a little bit patient. So one of the things that I like to do is to make an XY chart. I know this doesn't look like your typical XY chart because it's got X Then it has y with the function next to it so you can see how to calculate y. And then it says here's the ordered pair. So we're going to go through. One good thing about doing this is that you want to choose negative and positive numbers. You want to kind of think about numbers on either side of the origin so you can get an idea. And sometimes that's not good enough. Sometimes you're going to have to keep plugging in numbers so you can get values that are plottable. But we will have strategies that will help us around that. Let's talk about the values that we want. So I like starting off with -3, -2, -1, 0, 1, 2, and 3. I know that's a lot of points, but we need a good number of points to get a good shape on my parabola. So if I plug in -3, so -3 quantity squared, notice where my parentheses are, -2. If I square that -3, I get 9. -2 gives me 7. So the ordered pair that I'd have to graph here would be -3, 7. The next thing I have to do is plug in a -2. So I'm going to draw arrows. I know this is looking a little crazy. So when I plug in -2, I'm going to do -2 quantity squared -2. I'm going to get 4 -2 is equal to 2. So -2, 2 is a point. Let's do -1. So when I plug in -1 and I square it, I get 1 -2 is going to give me a -1. So this point is -1, -1. And finally, I'm going to plug in 0. You'll hear why I mean finally in a minute because you'll see something really nice happen. So if I put 0 in, I square it, I subtract 2, I'm going to get -2. The reason why I said finally is because I anticipated something. Realize that parabolas have a nice curve and they have a beautiful symmetry. So if you know what's happening on one side, you're going to know what's happening on the other side. Whether it's a, quote, upside down parabola or a right side up parabola. They all have symmetry. And they also have a name for this point right here. It's called the vertex. That's the vertex of your parabola. And so once you hit the vertex, you should already see something happening with your y terms. So we plotted some points. We've got -3, +7, -2, +2, -1, -1, 0, -2. Watch what happens when I put 1 into my equation. So over here I had -2, let me put that in. So when I square 1, I get 1 squared -2 is equal to -1. Notice that the answers that I got on this side of the 0 are going to be the same as the answers that I have on the other side. This does not always happen with 0, but there's always a time when this happens with a parabola. It might not be at 0 though. So I can comfortably see that I'm going to get 1. When I have 1, I'm going to have -1. When I plug in 2, it's going to be very similar to plugging in a -2 because I'm squaring it. When I square that -2, I'm going to get a +4 -2 will give me 2. So I'll get 2 here. So the point is 2, 2. And you guys should see symmetry happening. And if you don't see the symmetry happening now, you will definitely see it when we plot the points. When I plug in 3, I should put this here. When I plug in 3, just going to scratch that out. When I plug in 3, I'm going to get 3 squared. It's going to give me 9. 9 -2 gives me 7. So this becomes 7. So I get 3, 7. So what does it look like? Now I was being a little lazy. So here's the big reveal. This is what it looks like when I plot those points. Now I know that the text shows some other points, maybe a few less than we did, but we are going to see our points are here as well. So at -3, 7, 1, 2, 3, -3, 7, 1, 2, 3, 4, 5, 6, 7, you could see that these arrows are moving right up to that spot. -2, 1, so -2, I'm sorry, -2, 2, there's our point. At -1, -1, there's our point. At 0, -2, our point again. You guys see what I'm doing? You see what we did? And that's the power of the parabola. So the beautiful thing about a parabola and about quadratic functions is that there's a symmetry that lets us know when we've got enough points to get a nice shape, to get a nice curve. Are you guys ready for the next example? I'm sure you are. So let's look at this one. Here's example 2. We're going to make a table of values, then plot the ordered pair. So this is very similar. We would make a table of values, and what I'm actually going to do is just do a reveal on this one so you guys, well, no, I'm not. Let's do it together. So, because this is good. So let's go ahead. I'm going to do the same thing that I did. Let's do -3, -2, -1, 0, 1, 2, and 3. If I plug in -1, if I plug in -3, I'm going to get a +9, but that minus is going to make it negative. So when x is equal to -3, y is equal to negative 9. When I plug in negative 2, that's going to become a positive 4. When I put a negative in front of that positive 4, it's a negative 4. So in that case, y is equal to negative 4. Similarly, you can see that that'll give me a negative 1. Here I'm going to get 0 because you can't make negative 0 is just 0. When I plug in 1, I square it, I'm going to get 1, but then with that big negative in front, you see that I'm going to get to a negative 1. Similarly, these other values are going to be negative 4 and negative 9. So the ordered pairs that I would get would be negative 3, negative 9, negative 2, negative 4, negative 1, negative 1, and here's our curving point, 0, 0, and then we see that negative 1 comes right back up when I put in a positive 1. So then we see that we found our point of symmetry, or our vertex really, and later on when we get more mathy, we're going to be talking about something called the axis of symmetry when we deal with a parabola. So the big reveal of our graph would be this. Now the interesting thing is that this graph is a sad parabola. Can you think about what made this parabola go down? What would the C value be here? Sorry about that. What would the C value be here? Technically the C value is like 0, right? If I want the B value is 0, I'm talking about this if you don't know, ax squared plus bx plus c. Here the a value is negative 1. The b value, well, there's no other term, so the b value must be 0, and the c value must be 0. What did we say last time? Well, what did you think last time when we talked about how that negative 4 that's here, that is the c value, play out in our graph? And what do you think as we look at negative 2, which is the c value here, and how it played out in our graph? And what do you think, sorry about that, is going on here as we look at how negative, or how 0 plays out in our graph? And what's up with this negative sign on the A? How does that play out? So that's kind of what I'd like you to go ahead and play around with on Desmos and see if you can give me an answer to those questions. What effect does A have on our parabola? What effect does C have on our parabola? I have candy for the person who can come up with a really good idea of what's going on. So how can you investigate that? Create different kinds of equations that are quadratic and see the effect that different values of A and C have on it. More candy for the more thorough information that I can get. All right, let's do our final example. We got a little bit of time left. So Georgia threw a baseball into the air, and the equation that gives the ball's height in meters h as a function of time is given here. I'd like you to know that parabolas are, not parabolas, but quadratic functions are used a lot in physics and a lot in, well, a lot in physics when we talk about motion and the effect of, actually the motion of a ball being thrown is parabolic, and also the effect of gravity on an object has a parabolic, particularly when something's falling through the air or being thrown through the air. So that's something that you'll see a lot of. All right, so we're going to graph the equation and interpret the graph, and we're going to figure out the height of the ball. So I'm actually going to do a bit of a reveal on this. So we chose 0 for the time. So at time 0, we see that we're going to plug in 0 for time in each of these particular equations. Remember, h deals with the height at a particular time. So at time 0, the height of the ball was 1.4. So the height of the ball was 1.4 meters off the ground. Let's look at after 1 second. We see that the height of the ball is, again, we're going to put 1 into the equation. When we calculate it, we see that it's 12.4 meters off the ground. And so the ordered pair 1 and 12, I'm sorry, 12.5. 1 and 12.5 is being used here. After 2 seconds, plugging in 2, just as we did before, we see that after 2 seconds, we're at 13.8 meters off the ground. And finally, at 3 seconds, doing the calculation, we see that we are 3 and 5.3, well, we're now at 3 seconds, we're at 5.3 meters off the ground. So what's happening? That ball went up, and then it's coming back down. And so our graph can give us some indication of what's going on. So at time 0, the ball is thrown from this point, then it goes up, then it curves around, then it comes down. Now this curve is actually pretty gorgeous for only the 2 little points that are given here. So what I want you to do is make sure that you use enough points to actually get a really nice curve. So in the future you might have to use a few more points. Feel free to do so, that's okay. So what we have is we have this portion of the graph. What we need to do Okay, so basically, by plotting these points and by actually really we just needed to put this 3 in and get here. But by plotting these points, we can see the entire I don't know, spectrum of places that the ball has been in terms of its height during its travel. All right, I think that's it for me, guys. I'm going to let you go. Please see if you can answer those questions. I feel like giving candy away, and let me know if they make sense. I will talk to you soon. Let me know if you have any questions. Bye-bye. Thanks.